In this video, we're going to have a look at an optimization problem and how we can use differentiation to assist us. It's suggested that you pause the video here before we go through and have a look at the solution in detail. So when looking at a problem like this, let's have a look at the key information that we're being asked to find. We're being asked to find two counting numbers, and we want to find a product where the product is one of them and the square of the other to be a maximum. Let's have a look at the information that will help us. Obviously these two numbers are counting numbers. Their sum is 9, and we want to actually specify the product in an equation so we can go through and solve it. So let's have a look at how we set that up. The first thing we'll do is we'll let x and y be the numbers, and then we'll write the factual information. So we know that x plus y equals 9, and what we want to find is a product. So we'll list that product equation based on what we're given, and we'll call it x squared y. Now we could have said y squared x. The actual difference there is irrelevant because the equation, when we solve it, will take care of itself. So in solving an optimization problem, let's go through a basic checklist. What we need to do is write down any formula or equation relevant to the words that we've been given. And we also need to know what we've got to maximize or minimize. In this question, we've seen that we have to maximize the product, x squared y. But we can also see that if we're going to apply differentiation techniques, we have a little bit of a problem because we've got two variables. So another step in the process is to reduce our equation that we're trying to optimize down to one variable. And we have to ask ourselves how we're going to do that. So once again, we can see the equation we're trying to maximize. It's a product, which is the square of one number multiplied by the other. Now to eliminate one of the variables so we have an equation with just one variable, and therefore we can go through the differentiation process, we'll use our sum. So x plus y equals 9. And what we'll do in this case is we'll let y equal 9 minus x. And we can use that equation to substitute into the product rule. So if we do that, what we'll find is the product becomes as follows. P is now equal to x squared multiplied by 9 minus x. We'll expand that to get 9x squared minus x cubed. So this is the value that we're trying to maximize. We're trying to find the value of x that gives us the highest value for the product. So let's differentiate this, and we get 18x minus 3x squared. Now the reason we differentiate is because if we have some random part of a curve, we can see here that we've got a maximum point, and in this case we've got another stationary point which gives us a minimum. The derivative at the point which is stationary is 0. There may be other instances where there is a stationary point, and we may need to investigate further to test to see whether we've got a maximum, minimum, or neither of those two. So what we'll do initially is we'll put our derivative equal to 0. That means we're solving 18x minus 3x squared equal to 0. And the easiest way to do that is to factorize. So we'll factorize out a common factor of 3x, and we're left with 6 minus x. So for our solution, we can see that either x equals 0 to make this equation true, or 6 minus x equals 0, in which case x equals 6. Now at this point we could discard x equals 0 because it's not a counting number, but for the sake of this problem we'll carry through. Keep in mind that if x was equal to 0, the product would equal 0, which suggests it's probably going to be a minimum value for the product anyway. So once again we can see our two equations, the product rule, which we're trying to find a maximum for, and the derivative, which is going to assist us to find that maximum. Now we found beforehand that x equals 0 or 6 are the possible solutions, but what we'll need to do is find a second derivative to test them. So the second derivative is the derivative of the first derivative, and we get the following. Now if we substitute x equals 0 into the second derivative, we get a value of 18 minus 0, which is 18. Or more significantly, it's positive. And likewise, if we sub in x equals 6, we get a second derivative of 18 minus 6 times 6, which is equal to negative 18. Again, more significantly, it's negative. Now, if we go back to our graphs, which show us the extreme values, here is a maximum turning point where the gradient 0. The gradient is positive, 0, then negative. We can see that the gradient is decreasing. Now the second derivative measures the change in the first derivative. So that means the second derivative will be negative because it's seeing a decrease in the gradients. Likewise, if we have a minimum point, the gradients are negative, 0, then positive. The derivative will be increasing because the gradient's going from negative to positive. The second derivative, which measures the change in the first derivative, will be therefore positive. So we can see here that when we've got x equals 6, we do have a maximum solution that may be occurring. So let's go back to our original equation. We saw that x plus y was equal to 9. And we also saw that we wanted the product of x squared y. Now if x is equal to 6, we know that y must be equal to 3. And therefore our product equation is 6 squared multiplied by 3, which is 36 multiplied by 3, which gives 108. So going back to our original question, we had to find two counting numbers whose sum is 9, such that the product of one of them with the square of the other is a maximum. So the solution that we require is the two numbers. So therefore, the two numbers are 6 and 3. In some questions we may be asked to go through and actually give that maximum product. We've got it here in our working, but in this particular question all that was required was the two numbers to give that maximum product.